In this video, I'm going to be going through lift, thrust and drag calculations. Often what we're going to be finding is the lift to drag ratio, and there's four forces that we're interested in. Now there are different ways that this might be presented, but generally speaking, when we have our plane, we know that weight is always going to be down. Now I write this, I used to write it as W, but I like to write it as mg these days. So W equals mg, mass times gravity. I find that by writing mg, W can represent work, mass times gravity, well that's never going to be anything else. Mg, it also helps me to remember always multiply by gravity by seeing that g there. It means even if you somehow forgot to multiply by gravity, it's going to show the marker that you had some idea of what you were doing. Okay. The first thing and most important thing in this concept is you always want to remember that weight is down. It's vertical. It's the definition of vertical. Weight is, when we drop things, the direction that they fall is vertically down. Now, lift will always be perpendicular to the wings. So that will be defined by the angle of attack. For all of these questions, they're going to give you an angle of attack. I don't think there's a question where that's not the case. Now, the next thing to remember, so we've got four fundamental forces. We've got lift and weight, and we have thrust and drag. Thrust and drag always oppose each other, so that because they're collinear, we can represent these as one vector. Thrust minus drag can be represented as one vector. Now, there are some times where you'll see the HSC might write weight, in this case, lift, sorry, they might write it like this. They might draw it as a trapezium. That's something we can see. I don't like to do it that way. I like to take these forces and say, if this is weight, I'm much better at working with triangles. So I remember that this is weight, or mass times gravity. This is lift, and then this is thrust minus drag. Now, if we see a glider doesn't have any thrust. Gliders are dropped into the they're taken up into the air by a plane, and then they're allowed to fall with style, right? They fall very slowly, and we want as much drag as possible on a glider in order to stay up in the air for as long as possible. The other thing that occurs to me is that when looking at these questions, that I always thought, well, isn't lift up? And lift is up, but it's not directly up, it's not vertically up. It is in an upwards direction, but it's not vertically up. The next thing is I think, well, okay, well, if weight's down and lift is not as big, lift is not as big, then how do planes stay in the air? Well, they stay in the air because the thrust minus drag provides that additional vertical force and the vertical component of that force to help maintain equilibrium. Always remember with these questions, we're always looking at things in some form of equilibrium. So even though this plane is currently flying up into the air, we can consider that at this moment, at this instant, it's in equilibrium. So that's how we're going to approach this. Now, the first thing to remember is that we always have weight. I always draw weight first. I remember that weight, or mg, is down. It's vertically down, and it is always going to be the hypotenuse. Then lift will be an adjacent angle. It's going to be the next biggest, and then thrust minus drag is going to be the smallest. Now, there might be some, I can't imagine a situation where that's not going to be the case. I guess if a plane is climbing at more than 45 degrees, but that's not going to happen because we know that we would get wing stalling if we go over 20 degrees or so. So now at the end of these questions, I'm going to do 7 questions that are more or less in this format. We're going to do the 2007 question, which is level flight, and that's a simpler question. It's actually it's a moments question. It's not really this thing. And then we're going to look at a question that's a little bit different about don't be confused by the fact that it's a helicopter, but we're going to be looking at the reaction of the forces. But typically we're going to be looking at a plane, and we're looking at these 4 forces. All we're going to be doing is just over and over, we're going to be putting the same numbers on this triangle, and we're going to be using that to find, once we find this, we can then just calculate whatever the question's asked us to do. So without any further ado, we're going to do, this is the 2006 question. You can see it here, I don't need to write that down over and over again. 2006 question 15D. And in this question, they've asked us to determine the magnitude of the thrust required to maintain this aircraft in a constant climb at 20 degrees at a constant speed. Okay, so what we're going to be looking at is we've got our diagram. I'm drawing this diagram straight away. In this case, I don't need to do anything. Now, our angle of attack alpha, these angles, if I just make up another angle, right? If I say that this is beta, these two angles are equal because they're alternate angles on parallel lines. And then if we know that these are complementary, then these two have to equal. If these two equal 90, then these two have to equal 90. So that's just me establishing very quickly a proof that whatever the angle of attack is will also be the angle of this side of the triangle. So that's going to help us out quite quickly. In this case, alpha equals 20 degrees. So what we're going to do here is we've been given mg, and I find that students are often much better at handling trigonometry when it's drawn in this way. So if I say that we know in this case we have a weight, or mg, our mass is equal to 1,200 kilograms. So if we multiply it by gravity, we're just allowed to use gravity as 10. Now I will say in this situation we're dealing with such large numbers. This is one case where if your answers are off, it may have been because sometimes the HSE uses 10 and sometimes it doesn't. There's not much you can do about that. So we're going to say 20. So what we're trying to do is we're going to find this side first. We're going to find the thrust. Thrust minus drag. In this case, I'm only going to do the trigonometry once. So what we're looking at here is we've got the hypotenuse. This is the opposite. So we can say SOHCAHTOA. So we're trying to find the opposite. So we're going to say sine theta equals the opposite over the hypotenuse. In this case, the hypotenuse equals mg, so we're going to move that up here. We're going to bring up to sine 20 equals thrust minus drag. Okay, so if we apply that number, we've got 12,000, sine 20 equals, you've got that already? Just checking, I mean, always check that you're in degrees. So that's my thrust minus drag. Now, they've told us that there's 3 kilonewtons of drag. So we've said drag equals 3,000 newtons. So thrust equal, so I'll write as an equation, thrust minus drag equals so in this case, I can ignore this part, and I can say that what I need to do in order to make this equal, I have to bring this side over here. So I'm going to add 3,000 to both sides. So therefore thrust equals 7104 newtons. Okay, and that's what we had as our answer there. We're happy with that, we can move on. I do have a way. Now, this was a 3-mark question, so you had about 5 minutes to do that question. Okay, can we go to the next question, the 2008 question? Okay, could you just zoom in a little bit? Okay, and then down. Okay, so what we're looking at here. So here we're saying that our weight, which is down, is 85 tons. So we're going to write mg equals 85,000 kilograms, and then we're going to multiply that by another 10. So it's going to give us 850 kilonewtons. It's not the best 5 in the world, but it'll do. Okay, so then our angle of attack is 19 degrees. So that means this is 19 degrees. And now they told us any information. Determine the lift in this situation. Okay, well that's pretty easy. All they've asked, this is 2 marks, they've given us 3 minutes. This is lift. So in this case, lift is going to be cos, right? So we're gonna, I said I wasn't gonna do any more trigonometry, but cos theta equals adjacent over hypotenuse. So if we bring this across, we're gonna say mg cos theta equals cos 19 equals the adjacent, which equals lift. So lift equals 8,500 kilonewtons times cos 19. Have you got that already?
804.
804. Now, just a quick check. I look at this picture and it says, well, 804, this looks like it should be pretty close. We could actually do this graphically, just measuring. We would be allowed to do that if your calculator broke for some reason. You would be able to just draw something like 85 millimeters. And if you measured that this was 80.5 millimeters, you'd be able to say, okay, well, that's our answer, kilonewtons. And now you'll notice that our answer here, where are we, 15D. Oh, I didn't write about my answers, that's why. They've said 833. The reason why they've said 833 is because they probably have used gravity equal to 9.8. Okay, next one. Okay, so this time we have a plane that's landing, but always start by drawing our downward line for mass times gravity. So mass times gravity equals, in this case, 300 tons. So 300 times 1,000 times 10 newtons gives us 300 mg equals 300 kilonewtons. Okay, so now we're going to have, remember that all of our arrows need to go clockwise, or they need to all be going in the same direction. So in this case, they were all going relative to this dot. These arrows were all going anti-clockwise. In this case, they're all going clockwise. So make sure that for a vector diagram to work, because this is an equilibrium, all the arrows must be going in the same direction. So that can help me there. So what we're saying here is determine the lift to drag ratio. So we're going to need to know thrust minus drag, and we've got our lift. Now, calculate the drag while maintaining, oh, they've told us the lift to drag ratio is 8:1. Okay. So what we can do first is we can find lift, and then we can use our lift to drag ratio to calculate drag, and then from that we can calculate thrust minus drag. Okay, so in this case we're going to need both sides. We've got 5 minutes to do this question. No, 3 minutes to do this question, but we'll see how we go. Okay, so first of all, okay, so 3,000 kilonewtons, and what we're going to do now, we're going to find lift. So lift equals mg sine 15, which is 3,000 sine 15, which is what? 2,900. Okay. And that seems reasonable. It's not bigger than the hypotenuse, but it's close. And then what they've told us, the lift to drag ratio, lift over drag equals 8. So therefore drag equals lift divided by 8, which is equal to 2,900 divided by 8, gives us an answer of, what was that answer? 362.5 kilonewtons. And I've got 362 there, so that's good. Okay. So we can go on to the next one. Okay, so this is 2012, question 15D. Okay, so we've got another glider. Well, that one wasn't a glider, but it was descending. So this one here is, we're going to start with our mg, and our mg, we've told us that pilot has a mass of 83 kilograms, so it means we're probably going to calculate the mass of the glider. So we'll write it as mgt total. And we need to find the lift to drag ratio, and we're told that this is 15 degrees. And okay, they've told us the drag. Okay, so we said this is thrust minus drag. But in this case, if there's no thrust at all, in that case we can say that this is all drag. This is all drag. So first thing we're going to do, so we're going to set this as the, we know the drag. So what we'll start off by doing is we'll find mg total. So if we have the, we want to find the hypotenuse, we have the opposite. So we say so sine 15 degrees equals opposite, which is drag, over mg total. So we can rewrite that by saying, so the mg total equals the drag, which we said was 16 kilonewtons, divided by sine 15. Now this should be a number that's much bigger than, sorry, this is in newtons. After a while you get a general sense of what's reasonable. But there are very different scales of planes, so that can be difficult as well. 1600 newtons divided by sine 15 equals 6,000 and something. 6181, what's going to round up to 2 newtons. Now, we could play around with gravity, but we're just going to stick with, they're going to be very different answers depending on what value of gravity we've used. We're going to use the value of 10, so that's, well, we'll do both actually, because we'll do both. So that's our answer in newtons. So in that case, if we know that's our answer in newtons, what is that in kilograms? Well, the mass can either be, we divide by 10, so it's going to give us either 618.2 kilograms, or if we divide more accurately, divide by 9.8, that's going to give us 630 kilograms. Now, if we take away the pilot, so we can take away 83, the answer we're going to get there is 547, or 618.2 minus 83 equals 535.2. Okay, what did they want? They want this one here. That's the answer they want. Do they want the mass of the glider? Yeah, they want the mass of the glider. Calculate the mass of the glider. It's 535.2. And then we also need to calculate the lift. So lift equals, now that we know this value, we can write this one, 6182 sine 15. 6182 sine 15 equals 1600. I've done something wrong there. Okay, so this is where estimation can help me identify an error, because I know that this has to be close to the hypotenuse, and I had a number that was not close, right? 1600 is not close, so I knew that 1600 was our original drag, and that helped me to say, okay, well, I've made an error by doing estimation. 5971 is the correct answer. That's how many newtons of lift we have. If we want a lift to drag ratio, so lift divided by drag equals 5971 divided by 1600 equals 3.73, and that is our lift to drag ratio, and that's what we had on our answers there. Okay, we can go into the next one. Okay, so we've got 15 degrees up here, which means we've got 15 degrees down here. We've got thrust minus drag. We've got mass times gravity, and we've got lift. So what have they told us? It's 260 tons. So 260 tons, so times 1,000 times 10 is going to give us 2,600 kilonewtons. So it's pretty big, pretty heavy plane. You know, that's commercial for jet engine aircraft. It develops a thrust. They've told us thrust is equal to 987, and yeah, that's in kilonewtons, so just checking that everything's consistent, it's all in the same units. Okay, so what we now need to do is we're going to first figure out what our drag is, and then we can use that to find, if we go to find drag, find lift, and then find the ratio. So it's 3 marks worth about 5 minutes. Okay, so first of all, we'll find the total value of this sine, right? So we'll say thrust minus drag equals 2600 opposite hypotenuse opposite the angle, so sine 15. Okay. And we predict that this should be a number much smaller. So that's going to equal 672, we'll call it, round up to 3. Okay, so our thrust minus that amount of drag gives us this number. So our drag, our thrust is 987 minus our drag, thrust minus drag, so 987 minus drag equals 673. Okay, so drag equals 314 kilonewtons, and then our lift equals the same thing, mg cos theta, which is 15 degrees, which is equal to 2600 cos 15 equals 2511, and if we compare our lift to drag ratio, so lift divided by drag equals 2511 divided by 314 equals 7.999, which we're going to call 8. And that's the answer we get there. Okay, you can move on to the next one. Okay, so 2018, a two-engine aircraft, I can't see that, with a mass of whatever, can you see that number? Mass of 300, okay, so it's climbing, so it's going to look like this. So we've got mass times gravity, 330, so what we're going to do is multiply it by 1,000, multiplied by 10 gives us 3,300 kilonewtons of weight. Okay, each engine produces that much thrust. So we've got thrust minus drag. So our drag, I'm going to write that as 2 times 510. Now the reason I'm writing it that way is because I'm showing the marker that I know what I've at least acknowledged something going on. If I made a mistake after, the marker's going to show me something because I've at least written that. Okay, so complete the space diagram by completing the 4 forces of flight in this situation. So here they've shown us, I guess this dot is the center of gravity. So that's going to be mass times gravity, or you could just write weight, that's fine. This one here is lift. So we have thrust, and then backwards is drag. Okay, so we've got 2 marks just for doing that. Nice. Okay, once we've said determine the drag force induced for this situation, I think that's 3 marks. So what we have to do here is we have to find the thrust minus drag by finding the sine. So we're going to say thrust minus drag equals mg sine theta. It's sine. Okay, so which equals 3300 sine, what's our angle? 15 degrees? 15, 15, 15. So that number is equal to 854 kilonewtons. That number seems reasonable. It's not bigger than the hypotenuse, it's not close to the hypotenuse, it's much smaller. Okay, and then what we have here is we know the drag, so we know the thrust is 1120 minus drag. So it's this number minus something equals drag. So if we go 1120 minus okay, 18. Oh, there we go, look at that. I made a clerical error, but I probably would still have got full marks because I've shown very clearly where that clerical error has come from. Because I'd written 1120, because it's shown very clearly my working out, and there's so few marks, if I was marking this, I would be asking the senior marker, I would be saying, this student has demonstrated knowledge under a test condition. We're not going to penalize people for mathematical errors of that nature. That's what I would do. Anyway, the point is we got the answer right, which is, it's actually 116. So, okay, we can move on to the next one. This is our last one of this same format. No diagram this time, but we're going to draw a diagram anyway. I definitely recommend that you draw the diagram. Now, I will say that a lot of students I have who do these questions, they often don't really know what to do when it comes to lift. So this is where maybe I need to explain more clearly that we always want to remember that the lift is perpendicular to the wings, the thrust and the drag are collinear, and the weight is always down, and it's always the hypotenuse. Okay, 3,000, so okay, it's flying at constant level speed, okay, fine. And then using a free body diagram, calculate the thrust on the plane if the lift to drag ratio is 11. Okay, so we've got mg, they've told us that is equal to, so 30 kilonewtons, and we've got lift, and we've got thrust minus drag. Okay, 3,000, using a free body diagram, calculate the thrust on the plane if the lift to drag ratio is 11. Okay, so we know that this lift is equal to 11 drag. So what we can do first, we've got 5 minutes to do this question. So we've got lift is equal to, this is close, so it's going to be cos. So we've got 30 cos, I knew it was cos, I said it was cos and I started writing this. Cos, what's our angle? We don't know the angle. Okay, so, oh, okay, because it's at level flight. I got a little carried away. Okay, level flight means that the angle is 0. So in this case, the diagram, the triangle is like that. We can say in this case, mg equals lift. So we know what lift is equal to. Lift is equal to mg, which is 30 kilonewtons. And we then know that, so effectively we're going to have a force polygon that actually looks like this. We have mg, lift, all has to be going in the same direction, so this thrust minus drag. Okay, so the lift is 30,000, and then we know that the drag is 1/11 of that. So lift divided by drag equals 30 divided by 11 to 1. 2.727, which is 2.73 kilonewtons. Okay, so one's done. Okay, so this is also at level flight. But in this question, what they want us to do is they want us to find that it's a moments question. So on our plane, if we have our beam, what we effectively have is we have the weight of the plane, mg, which they've told us is 4,000 kilonewtons. They've told us lift, and then we have a additional force F. So this we've talked when I started teaching about couples, I used this same equation, which is earlier in the book, to talk about how if we didn't have the force on the horizontal stabilizer, we'd have an unresolved couple, and that would mean that the plane, if there's ever a difference between the center of gravity of the plane, or the center of mass, and the lift, there's going to be this, in this case, will actually be a clockwise spin. So we need something to counterbalance that. They've said that this distance here is 4 meters, and this distance is 40 meters. So if we just take some of the moments about, we'll call that x. So we'll say some of the moments about x equals 0. 0 equals, we can't do we know the lift? No, okay, they don't tell us the lift. Okay, in that case we're going to set x as this value, right? So x is the center of lift. So what we're going to say now is that we've got mg, which is 4,000, and it is 4 meters. But is it going clockwise or anti-clockwise relative to point X? Is that going clockwise or anti-clockwise? If this is our axis, so anti-clockwise, so we're going to make that a minus, right? And then we're going to have F, which we're saying relative to X is going to be clockwise. So we're going to have plus F40. So in this case, we're going to say that F equals 16,000 divided by 40, so that crosses out there, and so it's going to be 400. And it's going to have to be up. We made an assumption, down. We made an assumption that was down. Our number is positive, so 4,000 down. So 400 down. Okay. That one's done. Last question. Okay, so this question is interesting in that it's not asking about thrust. There's no thrust in this equation. So where we talk about thrust and drag being collinear, for a helicopter, it's a little bit more complicated. What we're going to have here is we're going to have a force polygon, where we always start with weight. We know that weight is going to be the largest vector in this diagram. So we've said it's 5.4 tons, so it's 5,400 kilograms multiplied by 10 gives us that many kilonewtons, so 54 kilonewtons, and that's going to be going down. Then they've said that we have lift. I'm going to actually draw this over here. We'll draw it this way. And then we're going to have lift. Yeah, okay. Lift at 70 degrees. So 54 kilonewtons. Then we're going to have lift of 58. And then we're going to have drag of 30. I think that's going to overshoot, 30 kilonewtons. And then we're going to need one additional force to close that vector diagram, something like that. Okay, so what are we going to do here? Well, first of all, let's find the difference in our verticals. So the vertical component, if we replace that 58 with the vertical component, what are we going to get? So if we have the vertical component of lift, we'll call that lift V and lift H. So what have we got there? That is based on 58 times 70 degrees. So this is opposite, so this would be 58 cos. Do you have that? This is sine, because it's opposite. How do I know that? Because the numbers don't look right. Since it's adjacent. So this is 19.84, and that's 54.5. So 54.5 kilonewtons up, and the horizontal component is 19.84. So what have we got left over? In order to bring this, to close this up, well, we know that this is going to be an extra. This missing amount here is 0.5 kilonewtons. And we know that this missing amount here is going to be 30 minus 19. Is 10.16 kilonewtons. So that means our resultant force. Now, are they looking for a resultant force? They're not looking for an equilibrium. So for a resultant force, what we look at is where we started. We started here and we finished here. All right, so we started here, we finished here. So we're going to be going that way. It's going to be 0.5 and 10.16. To find that, this angle here, theta, is going to be opposite. The resultant is going to be opposite over adjacent. So theta equals, normally I do the resultant first, but R equals the square root of squared plus 0.5 squared. Square root of that is 10.17. Is that plausible? Yeah, it is. It's only very slightly bigger. And all our values are in kilonewtons. And our theta is equal to opposite over hypotenuse. So 10.5. That's what I get. And when we look at the answers, it's pretty close to that. Okay. Yeah, this distance here may have been off camera, sorry about that. So, they're all the lift questions, the lift and drag questions, and the calculations that we get from past HSCs. Good luck.